All right, so we're going to do a second day of continuity where we see some more kind of AP style questions that they could ask you with continuity. And then we're also going to introduce the intermediate value theorem today, one of the very important theorems that you will be required to know for your AP exam. All right, so this is just that same definition of continuity we saw in our last lesson. F of C must be defined. The limit as x approaches C of f of x must exist, and that limit must equal f of C for the function to be continuous at a specific point. All right, so first example says use that definition of continuity to prove that the function is discontinuous at x equals 2 if a is equal to -4. Sketch the graph to check your answer. Okay, so what they're saying is that this is equal to -4x plus 7 if x is not equal to 2, and 1 if x is equal to 2. Okay, so I think we'll sketch the graph first, and then we can use our definition of continuity to prove the discontinuity afterwards. Okay, so what this is saying is that our graph is equal to this linear function for every point except for x equals 2. There's x equals 2, so there's going to be a hole in my graph where x is equal to 2. Okay, but everywhere else is this linear function. So we have a y-intercept of 7. All right, I don't like how narrow I made that, so I'm going to redo this. All right, there's 7 right there. And I'm going down 4, 1, 2, 3, 4, and right 1. So I can do that again, 1, 2, 3, 4. That's a -1. And right 1, there's going to be a hole in my graph right there. All right, I'll do it one more time. 1, 2, 3, 4. There's -5. And right 1. Okay, so I've got a line going through this and like that. All right, and then when x is equal to 2, my function is equal to +1. So 2, 1 is my closed circle right there. All right, so we have to use the definition of continuity to prove that this function is discontinuous. You can see that it's discontinuous on the graph because there's a hole in the graph. All right, this is a point discontinuity because it's discontinuous at a point. Okay, so if we do rule number 1, f of 2, where x equals 2 is our point of interest, f of 2 is defined. F of 2 is equal to 1. That's what they're telling us here on the bottom part. So it passes rule number 1. Rule number 2, the limit as x approaches 2 of f of x is equal to. All right, does it exist? It has to exist. And I would say yes, it does. The function is approaching, the function f of x is approaching this open circle from the left and the right. So the limit is equal to -1, which means it does exist. So it passes rule number 2, passes rule number 1, passes rule number 2. So that must mean rule number 3. F of x is discontinuous at x equals 2 because the limit as x approaches 2 of f of x does not equal f of 2. These two numbers are not the same. All right, that's rule number 3. Those have to be equal for the function to be continuous. All right, so we have proved the discontinuity using the definition of continuity. That's how you do it. Second one. All right, this one we are going to use the definition of continuity to find k so that f will be continuous at x equals 2, given this function. All right, so same sort of look, right? It's a piecewise function. We've got a constant in here that we need to figure out. And so, but unlike the last problem, we are trying to make this continuous. So last problem, they told us what that constant was. They told us a was equal to -4. And we were able to plug that in for a right there. Now they're not telling us what k is equal to. They're asking us to find it to make sure our function is continuous. Okay, put a star next to this one. This one is going to be on your AP exam for sure in some way. They ask questions like this all the time. Once we learn about derivatives, they're going to ask us questions like this again with referring to derivatives as well. So we're going to see questions like this all the time. Okay, so number 1 is that f of 2, x equals 2 is our point of interest. F of 2 must be defined. All right, f of 2 is equal to 5. All right, I have my equal sign up here on the inequality. So that means I plug the 2 in here. 2 plus 3 is 5. So f of 2 is defined, and it's equal to 5. All right, second part, the limit must exist. This is the key to this one. For our limit to exist, the limit from the left has to equal the limit from the right. So here's how we're going to do this. We're going to do a limit as x approaches 2 from the left. Now, if I'm coming from the left, I'm using the top piece because x is less than 2. That's left. So that's going to be x plus 3. Okay, I can solve this limit by doing direct substitution. I can plug the 2 in. 2 plus 3 is 5. All right, then I'm going to do the limit as x approaches 2 from the right. And so that's going to be the bottom piece because x is greater than 2, which is to the right. So that's going to be kx plus 6. I can solve this limit by direct substitution. Plug the 2 in, and I get 2k plus 6. Okay, for number 2 to be true, for the limit to exist, my two limits have to equal each other. 2k plus 6 has to equal 5. Subtract 6, 2k is equal to negative 1, k is equal to negative a half. There's our answer. Okay, and what we're saying is that if k is equal to negative a half, look what happens if I plug that in. I get 2 times negative a half plus 6. 2's cancel. Negative 1 plus 6 is equal to 5. See how our function definition is 5. Our limit from the left and the right are equal to 5. So that means rule number 3, I think I have some room down here. Rule number 3 is that the limit does exist. I just made it so if k is equal to negative a half, the limit as x approaches 2 of f of x is equal to 5, which is equal to f of 2. And there's rule number 3, that the limit is equal to the value of the function. All right, we can verify this by graphing, so let's do it. All right, if I plug in 2, I get 5. So 2, 1, 2, 3, 4, 5. Closed circle right there because it has the equal sign. Then we have a slope of 1. So I'm going to go up 1 and right 1. Oh, no, I don't want to do that because I have to go left. All right, x is less than 2, so I'm going to go down 1 and left 1. Down 1 and left 1 again. There's my y-intercept. All right, so that part of the graph goes like that. All right, and then if I rewrite this with my k plugged in, x plus 3 if x is greater than or equal to 2, and negative 1/2 x plus 6 if x is greater than 2. All right, so now if I plug in 2, I know I get 5. That's that point right there. It would have been an open circle, but the closed circle takes precedence and closes it in. All right, and then I can go down 1 and right 2. Down 1, right 2. And I could do that one more time if I like, but it's going to go like that. All right, could you draw this entire function without picking your pencil up off the paper? Certainly could. So it's a continuous function, and it's continuous at x equals 2, right there. All right, this one's a little tougher. Same idea, though. Use the definition of continuity to find A and B so that f will be continuous everywhere. Okay, so they just added another constant in there. Now we have to find 2 constants. Okay, so you'll kind of see what's going to happen here of how we're going to find both of them. Okay, so number 1. So what I started looking at, anytime I'm thinking of a piecewise function, I just kind of look at the function. So I have a horizontal line, I have a linear function, and I have another horizontal line. Okay, so all 3 of these functions on their own are continuous everywhere. A horizontal line is continuous the whole time, and a linear function is continuous the whole time. There are no holes, there are no asymptotes, there are no jumps. Okay, so the only places where discontinuities could occur are where they connect to each other or don't connect to each other. If they don't connect to each other, that's a discontinuity. So there could be a discontinuity at -3. There could also be a discontinuity at +1. So we have to check both of those locations. And we have to make sure we are going to find an A and a B that makes sure that they are continuous in both of those spots. Okay, so rule number 1 says that f of, and we're checking -3. I'm just starting with -3 because that's the smaller number. All right, f of -3 has to be defined. It is because there's an equal sign right here. F of -3 is equal to -17. Check. Rule number 2, the limit as x approaches -3 must exist. Okay, so we're going to do a left-hand limit as x approaches negative 3 from the left. From the left is going to be the top part, so that's negative 17. And the limit of a constant is equal to the constant. Then we're going to do a limit as x approaches negative 3 from the right. So that's going to be the middle one. X is greater than negative 3, if you kind of read that part backwards. So that's going to be the ax plus b. You can solve this limit by doing direct substitution, and you end up with negative 3a plus b. All right, for the limit to exist, our two one-sided limits have to be equal to each other. So negative 3a plus b has to be equal to negative 17. Okay, so this is the point in the last problem where we were able to solve the equation and get our answer. Okay, that is not possible right now because we have two unknowns, two variables. Anytime you have two variables, you need two equations to solve it. Okay, so that's where this x equals 1 is going to come in. So now we're going to go back up to rule number 1, and we're going to do this again, but we're going to do it at x equals 1 now. So now I want to know, is f of 1 defined? Okay, yes, I have an equal sign right there. F of 1 is equal to a times 1 plus b, which is equal to a plus b. Okay, rule number 2. The limit as x approaches 1 from the left. Okay, so that's where x is less than 1, so that's going to be the middle piece, ax plus b. So if I plug in 1, I can solve this by direct substitution. Plug in 1, I get a plus b. That matches up with f of 1. That's a good sign. We want everything to match, right, by the end of the problem. Okay, so now we do a limit as x approaches 1 from the right. All right, that's where x is greater than 1, so that's going to be the bottom piece, which is 3. Limit of a constant is equal to a constant. All right, so now we have a second equation. We have these two have to be equal to each other. A plus b is equal to 3. Those have to equal for the limit to exist. So now I have a system of equations. I have two equations with two variables, so I can solve this. I think what I'm going to do is I'm going to multiply this equation over here by negative 1. All right, that's going to give me a positive 3a. I'm going to write it over here. Positive 3a, negative b, and positive 17. Okay, then I'm going to take this equation exactly as it is, and I'm going to stack it right under here. A plus b is equal to 3. Okay, this is called the elimination method. Okay, the reason I multiplied the first one by a negative is because I wanted my b to be negative, which is going to cancel with the positive b. So what we're going to do with these two equations, we're going to add them together. 3a plus a is 4a. The b's cancel, which is what I wanted to happen. I engineered this for that exact thing to happen. And then 17 plus 3 is 20. That allows me to solve for a, which is 5. Okay, I'm part of the way there. Okay, now I need to get b. Okay, you can use either equation. I think this one's much easier right here. 5 plus b is equal to 3. So b is equal to negative 2. All right, this didn't ask us to graph it, but if we did graph our new function, negative 17, when x is less than or equal to negative 3, 5x minus 2, negative 3 less than x less than or equal to 1, and 3 when x is greater than 1. All right, if we graph that, we would see that it's a continuous function. All right, I'm going to pull up Desmos, and we're going to graph this. So I'm going to pause my video for a second, but I'll be back. All right, so here's a quick way to do Desmos. So y equals negative 17. All right, I need to zoom out a bit and maybe drag it. All right, there it is. All right, and if you want to have it on a domain, then you just put a brace like that, and then you say x is less than or equal to, negative 3. All right, and it stops it right there. All right, then y equals 5x minus 2. And then we want that one to be when negative 3 is less than x is less than or equal to 1. All right, and then one more, y equals 3. And we want that to be when x is greater than 3. X is greater than 1. There you go. So you can see that all of these do attach to each other right there. And so I could draw that entire function without picking my pencil up off the paper. It's a continuous function. All right, last thing we're going to talk about is a quick introduction of the intermediate value theorem. It's a very important theorem. You will definitely be asked to use this on the free response part of your test. I say definitely. It's not on there every single year, but it is a common question that is asked. So you definitely want to know how this works. Okay, so here are the properties of the intermediate value theorem. First one, very important. You must state this every time you use it. F of x is continuous on the closed interval a to b. So you can only use this if f of x is a continuous function. All right, number two, I really don't use that all that much. But your two y values, okay, these are y values, have to be different from each other. Okay, if they're not different from each other, it doesn't work. All right, and then they're going to give you a y value. So if k, this is given in the problem. So if k is between your other two y values, then that means that there exists a number c that is between a and b for which f of c is equal to k. All right, so that conclusion is a little confusing without a visual. So let's look at a visual. Okay, so you're going to be given some sort of interval, a to b, on the x-axis, x, f of x. Okay, so we'll put a couple points here, and up here. So the y values that correspond are f of a and f of b. And they can't be the same. So if I had drawn my B point right there, right in line, that wouldn't have worked. Okay, they have to be different. Okay, and so then we have a continuous function between those 2 points. Okay, it can look like anything you want. There we go. Continuous function. All right, so then there exists a c. So now you're given a k. So I'm just going to put a k on my y-axis right here. That's something that you will be told in the problem. So you're given a k, and what the intermediate value theorem says is that if k is between these two numbers, then that means that there is a c value in between a and b that corresponds to that. Okay, so if I were to map this over, I would get to that point right there. And if I were to map this down, okay, I'm drawing this out by hand, so it looks a little close here, but there would be a c right there. So if that's x value c, then that means I can say that this point is f of c. And that's what they're saying at the end here, that f of c is equal to k. Okay, so all it's saying is that if there's a y value between these two y values, then there must be a corresponding x value between these two x values. That's what it's intermediate value. It's in between. All right, so it seems like a lot of words and a lot of confusing stuff, but it's really not too bad. Okay, we do have a nice way to write it out to where you don't have to write too much. Okay, all you have to do is remember the name of the theorem and a couple of pieces of information that you have to put down. Okay, so everything I just said is described here in this sentence again. All right, so let's try a problem to finish up our notes here. All right, use the intermediate value theorem to show that f of x takes on the value 1. There's your k. Takes on the value 1 for some interval -2 to 4. That's your a and your b. Okay, so before we start any work on an intermediate value theorem problem, first thing we have to do is we have to state f of x is continuous. Sometimes you have to think about this a little bit more. Our function is a polynomial. That means it has x raised to powers, and there's multiple terms. Okay, all polynomials are continuous everywhere. They never have a hole. They never have an asymptote. Okay, when we do other problems like this, you may get a function with a denominator. So if it has a denominator, that's always something you have to think about. Okay, is there a hole? Is there an asymptote? Is there some sort of discontinuity? Okay, polynomials never have a discontinuity. So this is actually good enough, but I do want you to get in the habit of saying f of x is continuous on the interval. So on -2 to 4. Because if it's not continuous everywhere and you don't mention the interval in your answer, then you've actually said something wrong. Okay, so we're going to do more intermediate value theorem tomorrow, and you'll see what I'm talking about more there. Okay, so we have to state that in the problem. It's not implied. You must explicitly write it down. All right, second part. Now we are going to plug these two numbers in to our function. Okay, and we are going to get out some y values, and then we are hopefully going to be able to write an inequality using our k over here. All right, so f of -2. So that's -2 cubed minus 3 times -2. So that's -8 plus 6. which is -2. F of 4, that's 4 cubed minus 3 times 4. So 64 minus 12, which is 52. Okay, so what has to happen is that this k that they've given us in the problem has to be between those two numbers. And it is. So we're going to write this out as an inequality. Okay, I write a little bit more than is required, but I want us to write our answers so perfectly that they have no choice but to give us the points. Okay, so I'm always going to encourage you to write a little more than you have to on these problems. So I know -2 is my smallest number, so I'm starting with that, and that's equal to f of -2. So I'm going to say f of -2, which is equal to -2, is less than or equal to 1, which is the number they gave me in the problem, and 1 is less than or equal to 52, which is equal to f of 4. That's the key right there. So what's going to earn you some points? Stating that the function is continuous on the interval, you're going to get a point for that. Setting up this inequality. I had us write down our work here. We could have found those in our head. If you're good at calculating stuff in your head, if you're not good at calculating in your head, write it down, just like I did in the notes. But we don't have to write these down. This inequality is good enough. That's going to get us that point. Okay, there's a third thing we have to write down. Therefore, these triangle of dots, this means therefore. IVT, we're going to abbreviate intermediate value theorem by the first letters. IVT applies. And that is going to earn us the third point there. So those are the three pieces you need. You need to make sure you state the function is continuous on the interval. You need to make sure that you put your k in between two y values in an inequality. And then you need to make sure that you invoke the name of the theorem at the end. IVT applies. If you've done those three things, they have no choice but to give you all the points on that problem. All right, that's it for this one. I will see you for some more intermediate value theorem on our next video.